Thank you, Peter. Thank you very much to the department for the invitation. It's a pleasure to be back. It's kind of the second part of my stay, which started last year, and in fact, what I'm presenting also partially was done here and perhaps triggered by a question by Tom Spencer. So Peter already mentioned the title, so it's a critical drift-diffusion process or equation. And I'd like to point out some intermittent behavior and in particular connect to canonical diffusion on the group of matrices of determinant 1, 2 by 2 matrices, so SL2. And so what I'm talking about is joint work with Peter Morphy, who's sitting in the first row. He's an NSF postdoc in Leipzig, and Christian Wagner, who was here with me last year. And we posted this just a couple of days ago on the archive, which as some kind of lecture notes for this course. So you may read up a bit there. It's fairly short, 20 pages or so, and and it's based on earlier work with Georgiana Georgiou. Was in Leipzig and now is back on Cyprus, and Lihan Wang, who also was in Leipzig and now is at CMU. So let me start by with the introduction, and I don't think I will be getting much further today, and giving you the setting of the problem. I want to, in a certain sense, I'm specifying a very, I'm looking at a very specific problem which I would like to introduce. So I start with the drift diffusion process. In RD or R2, to be more specific, I point out when two dimensions will play a role, and they do play a role at some kind of important moments. So I write it in the way stochastic analysts would write it, but that's for the moment actually not really important. So there is the drift part in a vector field B, and there is the diffusion part, which is driven by two-dimensional Brownian motion, and I'd like to use the analyst convention in such a way that the generator of this process is this first order operator which comes from the drift, and 1 times the second order operator which comes from the diffusion. And the important assumption is that the drift is time independent and divergence free. So let me kind of put that very clearly here. So B is just a function of the spatial position, and the divergence of B vanishes identically. And in fact, in fact, the main object we're going to look at is going to be more on the PDE side, and let me kind of introduce this right away. We consider the expected position. So expectation is with respect to the Brownian motion, the driving Brownian motion of the particle at time t, conditioned on the fact that it starts at x let me give this the name uxt, and it's characterized by so it's characterized by the parabolic PDE dtu minus the generator of u is equal to 0, and initial data which are given by the identity. So you may think of this map as something like Lagrangian coordinates, which however are averaged with respect to the thermal noise. But still it's kind of convenient to think of this as being a time-dependent map from position space to position space. Okay, and most of what I'm going to say will be really about the solution of this PDE. And now comes the second main assumption, namely that we want to look at generic drifts, and generic here means random. And kind of in a certain sense, the most random way we could do is to say that B is some amplitude epsilon times the L2 orthogonal projection onto divergence-free fields of white noise. So eventually I will have to modify this a little bit, and I will make it very precise. But what I mean here, because this is too rough, but for the discussion, for the beginning discussion, that's a good way to think about it. That you take vector valued white noise, you project it onto the divergence-free fields in a distributional sense, and then you endow it with an amplitude epsilon. I'll get back to the meaning of this. So that's kind of a probability measure on drifts, which is clearly Gaussian, centered, stationary. Stationary means that it's invariant in law under spatial shift. It's also isotropic, which is a property that will be important eventually. And in fact, one way to normalize it is as follows, by looking at the covariance function between bx and by. And in order not to have at this stage to deal with the divergence-free condition, let me contract it by looking at the inner product between these two tangent vectors. And the normalization is, so there has to be an epsilon square because of the white noise character. It's a Dirac of x minus y, and the normalization is 2 pi because that's convenient on the level of Fourier. Okay, so this is the setting. So you can either think about it on the level of the stochastic drift diffusion process, or you can think about it on the level of this parabolic equation, which has kind of a random first order term, which is the vectorial heat equation plus a random first order term. So that's the setting, and now I'd like to come up with some heuristics. So that would be of what to expect. And now let me start by saying let's momentarily forget about the diffusion. So if we ignore diffusion for a moment, then this is just a fancy way of saying that u indeed are the Lagrangian coordinates, the particle coordinates, or of saying that this is the flow map of the vector field B. And then elementary calculus tells you that if we monitor the gradient of these coordinates along the particle which, let's say, at initial time was at the origin, over time, then this time-dependent vector satisfies a simple ODE, a simple linear ODE, which I can write like this. That's a consequence of the chain rule. And now the order may seem, unusual to you. This is because for later purposes it will be convenient to think of this symbol here as a as the differential, which means a cotangent vector, whereas u and b are tangent vectors, so that the usual gradient would be the transpose of this quantity. So that's a little bit a misuse of notation. If you want that we we write something as a gradient, which in fact is the transpose of a gradient. The only reason for this is that the order of this matrix multiplication is such that this driver comes second, which is more reminiscent of what you would do in stochastic differential equations. So this is, I hope it will not confuse you too much. That's just so in the sequel also I will always kind of carefully distinguish between tangent and cotangent vectors, because that's eventually helpful, because we're looking at SO2 invariance, so it's good to think about the objects not really as matrices, as collection of numbers, but as endomorphisms. So we'll see later on that this is kind of convenient. Okay, so, and of course, at time t equal to 0, it's the identity. And then there is a simple identity which tells you that if you look at the determinant of this matrix or endomorphism of cotangent vector space, it satisfies also a linear equation where I have to take the trace of this driving matrix field, and of course the trace of the derivation is the divergence, and that was assumed to vanish. So that means the determinant doesn't change over time. Initially we started with the identity, so this implies that the determinant of this map stays 1 all the time. So so that means a fancy way of saying is that this is an element of the special linear group in 2 space dimensions, and this is an element of the, so that's a Lie group, and that will play a role a little bit later, that this is an element of the Lie algebra. And so now in a certain sense the heuristics which I want to explain is that rather than kind of looking at this equation at bare face value, or rather this one, you should think of it as being kind of a stochastic differential equation. So think of star as a stochastic ODE of the form d grad u 0 t is equal to grad u 0 t times the driver dB. And now I think for today it's not yet important, but eventually it's important to make a difference between Stratonovich and Ito. Stratonovich and Ito's notion of differential equations. Now here, for the moment, we'll interpret this in the Stratonovich sense, if you don't know what it means, it just means what you would get naively if you would regularize a noise, if this should be white noise. So, but for the moment, just think about it. Don't think about it too much. Okay, so where, unfortunately I have to continue this sentence over here. Where we'd like to simulate the B, which in order to be identical with this equation, defined through dBt is equal to gradient of B, or differential of B at xt dt, and with initial data being 0, with a Gaussian process with independent increments, with centered, stationary, and independent increments. And so that's the, in a certain sense, the main task that we want to understand. We want to understand this process better, and we want to understand how this picture, for which we had to ignore diffusion, survives in the presence of diffusion. So that's the that's what I want to explain. So now in the rest of today, I would like to kind of lead you to the main, motivate the main result. And in order to do so, I will now, kind of write down 3 facts, which if I have the time, I will check for you. If I don't have the time, they're really elementary. And I will put them together in order to get a better idea of what this object and then what this object should be. So, and again, those facts are fairly elementary. So fact 1 would be, if x bar is the diffusion with generator, let's call it L bar, equal to lambda times the Laplacian. So what I want to do in a second is I want to compare this drift diffusion generator, which is here on the lower blackboard, to a constant coefficient generator, an enhanced diffusion generator, so enhanced diffusion generator. And I want to, at this stage, just do this, and then I want to tell you how this constant can be chosen, or must be chosen in a self-consistent way that we get the right heuristics. So for the moment, this operator is not at all related to this one, and eventually, anyway, lambda is not a fixed number, but something which changes over time. So, but let's look at it like this. So this is diffusion with this generator, and let's say we start at the origin, and we define very much in this spirit a process d bar as the expectation of this quantity here. And so So here we take this this process which arises from the constant diffusion. I plug it in like we did here. Now it's the x bar, and now I take the expectation with respect to the Brownian motion which drives this this process. So this expectation always is with respect to the thermal noise. As opposed to when I mean this, and that's the expectation with respect to the ensemble of B's. So, so hopefully that will help me to kind of distinguish these two things. So if this is the case, then a simple computation leads to the following statement. If I now look at this process at time t, and I look at its squared Frobenius norm. So this is a matrix, so I look at the sum of the squares of all its entries. And it's convenient to put the factor 1/2 here, and then I take the expectation with respect to the b. Then I get a clean formula, which is epsilon squared over 4 times lambda t. And here I have to take the time derivative. So this formula monitors how kind of the size of this matrix, which is defined by this equation here, changes, how the expectation of the size, the squared size of this matrix changes over time. And it gives a formula in terms of this diffusivity and in terms of time and the amplitude, or the square of the amplitude, which is sitting here. And the fact that it goes like 1 over t, which when you try to integrate this would give you a logarithm, is a consequence of the fact that you're in 2D. Okay, so that's the first formula. And the first fact, again, if I have the time, I can sketch the proof. The second fact I need in order to explain, to give you the heuristics of the result. And that's something we'll make more precise in lemma, which will be lemma 1. So if B or B bar is the Brownian motion on SL2, on the Lie algebra SL2, so on the space of all 2x2 matrices with trace 0, which is normalized by a similar condition by stating, by looking at the Frobenius norm. Now I call the variable tau. I again look at the square with a 1/2, and I say I want the normalization that this is equal to tau, very much like Brownian, like what you would do without the 1/2 for Brownian motion in usual Euclidean space. But anyway, this is a kind of a linear, or if you want a Euclidean space. So if you have, if you look at this object, and you look at a solution of this type of equation. So you look at df is equal to f Stratonovich dB with initial data given by the identity. Then there is a clear formula, which is a little bit surprising because you're working in a Lie group. But if you look at the Frobenius norm of this matrix of determinant 1, it behaves like e to the power tau. So it's a little bit like geometric Brownian motion, that if you solve this tensorial stochastic exponential and this was the usual Brownian motion, then the geometric Brownian motion grows exponentially in tau, and you get this this formula if you had this normalization, and a couple of more conditions which are made more precise in the lemma, because in a certain sense this condition doesn't yet completely fix what this Brownian motion is. There are a couple of more kind of canonical conditions which fix this Brownian motion and for which you have this formula. So that's the fact number 2. And now comes the last fact. And with this one I can explain what the heuristics will be, or what the result should, what the type of result should be.
Is the formula valid at tau equals 0?
I'm sorry?
Is the formula valid at tau equals 0? What's the one?
This one here?
Yeah.
Yeah, so at tau equal to 0, you get the identity. So the Frobenius norm of the identity in 2 space dimensions squared is 2. So the 1/2 just compensates for that.
Okay, thank you.
In fact, you know, I mean, you can also, I mean, because of isotropy, you can also kind of formulate it in a different way, but for the moment, that's kind of the, a convenient way of putting it. And you know, in what I'm saying, constants do matter. Yeah, so the fact that here you get a constant 1, here you get a constant 1, will be important. More questions? Okay, so fact 3 is the following. So now let's look at the objects we're looking at. So so that means X is the drift diffusion, so our drift diffusion process. So with respect to the generator, L is equal to B nabla plus Laplacian, and U of xt is the expected position, sorry, that's a symbol E, so the expectation with respect to the Brownian motion of the particle at position t, conditioned on the fact that at position 0 it's in the point x. And it's also convenient to look, so this, if you want, our average Lagrangian coordinates, and it's also convenient to look at the corresponding displacement. So how far have the particles moved? And I will always call this quantity phi, because there, as I will be able to explain at some point, is a connection to what's called the corrector. And so if you look at these quantities, then there is a convenient formula. If you monitor the second moment of the of this drift diffusion process, and you look at the at its annealed version, then you can describe how it changes over time with help of this U, and that's given by the expectation of the gradient of U at time t. And this is a stationary quantity, so it doesn't matter where I evaluate it. So let's evaluate it in 0. And this is almost true. I have to kind of get rid of something which will turn out to be, or which you should think at this stage as being lower order, which can be formulated in terms of the square of this corrector. So the time derivative acts on these two quantities. And again, that's a simple formula which, if I have the time, I can explain how it's derived. So now let's for the moment accept these three facts. So the first fact is kind of a statement on our type of driver if we plug in a much simpler process and take the expectation with respect to the thermal noise that drives this process. Then we get this, this formula here. The second is kind of more of a geometric statement. When we have something like a canonical diffusion on SL2, then we know how the Frobenius norms, or norm in the ambient space, evolves in time. And the third statement is something which relates the evolution of annealed second moments of the process to the gradient of this Lagrangian coordinates. So what do we learn from this? And that will allow me to kind of state the main result. So what we learned from fact 1 is that if we define B bar as it's done there, then, provided we perform a change of time variables, which we read off from this factor, we get a process which behaves like this process. So, in other words, then, loosely speaking, B behaves like Brownian motion, like this object here, under the change of time, which is given by d tau is equal to epsilon square for lambda t dt. So that's the infinitesimal way of relating two timescales. The timescale which we want here for this normalization, and the timescale which we get from this formula. So that's what we learned from fact 1. And from fact 2, we learned that if f is defined like this, with the b which we get from this change of time, which is not quite Brownian motion, it doesn't have independent increments, but it should be somehow, morally speaking, close to Brownian motion, we should get this rate of growth. So the expectation of 1/2 f tau square is approximately to e tau. And now, what do we learn from fact 3? So let's write down fact 3 on this side of the blackboard. So ddt of the annealed second moments of our process minus the square of, let me call it the corrector, is equal to the expectation of the gradient of u squared. So since grad u of 0t satisfies a very similar differential equation, we expect this here to behave like the expectation of f squared, which we know how it behaves in tau with a factor of 2. It's e to the power tau. This here, if the constant lambda is chosen the right way so that the two processes, and we'll have to get the condition that this is the case, so that the two processes are similar, then this should be equal to that. And that is something which can be expressed in terms of lambda by the usual formula for the second moments in two space dimensions. That's the 2 for the space dimension. And this one, that's neglected in the tradition of neglecting the size of correctors in this type of homogenization argument. And then if you believe this formula and you say, okay, so we'll learn that lambda has to depend on t, but for a moment let's ignore this, so the time derivative falls just on this t, you learn that lambda is approximately equal to e to the e tau. And now we combine this with the change of variables. So let me write this down. D tau is equal to epsilon square over 4 lambda t dt. And I claim that from these two identities we now can infer how lambda has to be kind of adapted to t for this picture to be self-consistent. So let's do that together. By deriving an ODE for lambda, so d lambda dt, kind of what's the effective diffusivity as a function of time. So the effective diffusivity, the rate of change of the effective diffusivity, I write it like this. So that's the chain rule. Then I use the first identity to write this here as lambda, and I use the second identity to write this here as epsilon over 4 times. There's a square missing. I'm sorry. There's this. I forgot the square already here. So there's a square here, and now it's important that there is a square here. And now you see that, okay, so this cancels, and you bring the lambda on the other side, and you bring a 2 on the other side, then you get an ODE for lambda squared, which goes like essentially 1 over t. So you integrate it up, you get a logarithm. So what you find is that lambda should behave like 1, which is the bare diffusion, epsilon squared over 2, logarithm of t square root. And now you also learn what the tau is. So the change of time scale should be double logarithm. So logarithm of lambda, so logarithm of 1 plus epsilon squared over 2 over t. So, so this heuristics tells you that on the one hand there is a self-consistent definition of this time-changing effective diffusivity for the process, and there is a self-consistent change, change of time variables, which should connect what we're interested in to the diffusion, to this, what I will point out, standard diffusion on SL2. So let me now state the kind of main result, which is motivated by these heuristics. So what I have to do, so there's, I think in a certain sense Peter's question may have already been related to this, or perhaps you already see it here. This is too singular to integrate it up from 0, time t equal to 0. So clearly this problem, and that's very well known, has kind of a small scale divergence. This assumption of having white noise, of the drift of being white noise, is just too rough. So we need, in order to give this a sense, it was good to have this ansatz for the heuristics, because then you see things more clearly. But if you want to make a rigorous statement, you in a certain sense learn here that you need a small scale cutoff. And we do that in a very primitive way, and it doesn't really matter which way you do it. We do it by Fourier projection. And by a very simple Fourier projection to fix ideas. So we introduce a UV ultraviolet cutoff by saying that on the level of the Fourier transform, and if we look at the Fourier transform of our drift at the wave vector k, and this, so since constants matter, I'll be precise of what my normalization is. This is defined to be what we had before. Let me just call this k old, and I'll eventually write down kind of the full covariance function. And now we take away all wave numbers which are larger than 1. So that's a very kind of brutal way of smoothing out everything. You cut away the high k's, which means you project on scales which are larger than 1. So in a certain sense, we've normalized our cutoff scale to 1. Of course, we're free to do so without loss of generality, because it's we can non-dimensionalize length like this, and which, however, means that the epsilon, which I introduced before, now is a true non-dimensional parameter, and in fact, in applied in kind of convection-enhanced diffusion, the epsilon goes by the name of Pickley number, because it kind of relates the strength of convection to the strength of diffusion. So that's just a name. So this is how I have to change the definition of the drift field B. And now let me give you the full definition here. So we first redefine F with a shifted starting time. So let me call this tau tilde. You will see why it's convenient or good to have this flexibility. And I think perhaps this fits better here. And the way we define it is by df tau star comma tau is equal to f tau star comma tau with Stratonovich driver dB for tau larger than tau star, and f tau star tau is the identity for tau less than tau star. So we have a certain amount of waiting time. We start from time tau star. It's the identity up to there, and then we start with the b. And where b is Brownian motion on the Lie algebra, so the trace-free matrices, 2 by 2 matrices, which is made unique by 3 postulates. The first postulate is that B is, the law of B is invariant under conjugation by SO2. So I formulate this a little bit carefully because it's not just, right multiplication, but it's really conjugation. The second statement is that the second kind of requirement is that it doesn't matter whether we define it via Ito or via Stratonovich. So this was Ito. This is Stratonovich. And next time I will explain this in more detail. What the difference is, I hope I give you some intuition. This is Ito. And the second claim is that the Brownian motion has to be defined in such a way that Ito is equal to Stratonovich. And the third one is the normalization we had, namely if we look at 1/2 times the Frobenius norm squared, then we get tau. And the lemma is that this determines B and F uniquely in law. And now comes the theorem. So that's with Peter and Christian and myself. So that's something you find in the post. So there exists a coupling between, if you want, the environmental noise, B, this kind of drift field whose distribution is defined here and what I said before, and the capital B, which is the driving noise for this diffusion on SL2. And essentially, I almost described what the coupling is, such that for all spatial points x and for all time horizons t, we have the following statement. If we look at increments of u, so u of x comma t minus u of 0 comma t, so that's an increment of this field u, these Lagrangian coordinates, these averaged over thermal noise Lagrangian coordinates, and we compare it to this matrix valued process applied to x, and because of our strange convention, I have to take the transpose or the dagger here, and here I have to tell you what the indices are in a second. And we look at the second moment of this quantity. We divide by x squared. We integrate we take the time average from 0 to capital T. And we take the second moment. Then this is smaller than epsilon square times the expectation of f tau. Now I take the Frobenius norm. And so let me put a bit more space here. So the time here, not surprisingly, is given by tau of t, where the relationship between tau and t will be defined almost like this. I will write it down in a second. But the initial time is something which depends on the modulus of f. So this is minus f dagger tau of the modulus of x squared. So, so when you start this process by which you compare, depends on how far these 2 points are you build the increment over. And so the statement, so let me define lambda of tau, where tau of t is defined exactly like we heuristically derived it here, just with a t plus 1. So logarithm of square root 1 plus epsilon over 2 logarithm t plus 1. And I should put a general argument s here, because we're using it for s equal to t, but also for s equal to x squared. And now if, since this is the same coupling for all points, you can also let x go to 0, and then you recover what we were guessing before, namely that the expectation of the time average of the gradient of u at 0t minus f starting now at 0 tau of t squared is less than epsilon squared times the expectation, the second moment of this quantity, which indeed means that at least for epsilon small, so for small Peclet number, this quantity is close to that quantity. Okay, so that is kind of the main theorem, which in the course I want to explain better, and I want to give you some ideas of the proof, and I want to draw some consequences. And I guess one interesting consequence of this is that this process here is strongly intermittent. It's, I mean, as you can see from this definition, it looks a little bit like a stochastic exponentials. Stochastic exponentials are known, scalar stochastic exponentials are known for, the fact that they're non-tight. The expectation has one value, but pathwise the trajectories converge to 0. And now this is not, this is in a certain sense not the standard stochastic exponential, because it's tensor valued. Here, those are elements of SO2. That's an element of the corresponding Lie group, or those are 2 by 2 matrices. So the arguments which allow you to understand the stochastic exponential in a very explicit way don't right away apply. But still, you can see from this formula that certain aspects, certain projections of, well, not this formula, but the one which was somewhere earlier with the exponential. So this here was that the expectation of 1/2 f tau square goes like e tau. That some of these things are fairly explicit, and in fact there is a way of comparing the squared Frobenius norm to a scalar stochastic exponential, and from this property we'll derive intermittency properties of this f, which then translate to grad u, or more importantly to the increments of u, and which a little bit reminiscent of fluid dynamics will give you the fact, will tell you that different pth moments of increments kind of give different modules of, the modules of continuity, which you get, which is borderline Lipschitz, but not quite Lipschitz because of this dependence here. The power of the logarithm depends on the stochastic moment you're looking at. And so that's perhaps an interesting analogy to kind of certain questions in fluid dynamics. And I think my time is almost over. And okay, so let me tell you what the plan now is. So this I hope gives I wanted to tell you what I want to explain in this course in the first of these 4 sessions. I guess next week I'm happy to first of all I'm happy to take your suggestions, what you find interesting, what you want to see. So I can go back to these 3 facts, which I mentioned, and explain them in a bit better way. But if in principle my plan was to tell you more about this natural notion of diffusion on SL2, which is triggered by canonical choice of diffusion of Brownian motion on little SL2, and work out what I said, kind of this comparison to the standard stochastic exponential. Then, equipped with this, I want to kind of get to some corollaries of this statement, working out this intermittency. So the fact that if you look at pth moments, you get kind of anomalous behavior, and then if perhaps the last or the previous to last session, I'd like to explain to you a little bit what's involved in the proof, and the main idea is kind of a stochastic, in a certain sense, a stochastic homogenization result, a scale by scale stochastic homogenization result. For instance, in the spirit of Brickmoint and Kupiainen for non-divergence-free drifts, we use kind of a similar approach to derive these error estimates between the solution of the PDE with a random drift and this matrix valued, this SO2 valued process. That's the plan. So now stop.
We should have questions. Are you gonna show us how to construct the Brownian motion, or so is there an existence, constructive existence result as well?
Yes, but I think in a certain sense existence is not so much the issue, because it's it's a finite dimensional stochastic process, and to which the general theory applies. I think more important is the fact that these properties uniquely characterize it. So my focus was more on kind of characterizing the process.
You have to construct it with that property.
You have to, yes, so that's correct. And but I think what's more interesting is how do you go from this environmental noise, this quenched noise, so to say, to the B, and that I think will come up in a quite explicit way.
Just to piggyback off Peter's question, basically. So what goes wrong in this lemma 1 there if I just pick B to be kind of what I would think of if I just view SL2 as a vector space, right? So I can view little SL2 as like a vector space, and I can take an orthonormal basis, and I can just put some real valued Brownian motions in front of them.
Sure. So I mean, indeed, this is a 3-dimensional vector space, and kind of fixing a Brownian motion amounts to a choice of an inner product on this 3-dimensional vector space.
Yes.
And so now, because you insist that the Brownian motion is SO2 invariant, you have two free parameters. That's a little bit of elementary representation theory. And now you fix these two parameters by making these two statements. So if you didn't insist on Stratonovich equal to Ito, you wouldn't be able to use martingale properties, which are very powerful. So here you have martingale properties. The Stratonovich form, in fact, ensures that that this defines something in the Lie group, because only for the Stratonovich notion of stochastic differential equation, you have the chain rule. So you need to play with both sides, and so in that sense, it's canonical. But the other answer would be, we have to make this choice because otherwise this theorem wouldn't be correct.
But is this choice the same as taking the inner product that's induced by the Lie group, SL2? Because I have my Lie algebra, I have the natural one like SL2, I guess, which would be the trace of A, B transpose.
So I think it's certainly a natural choice under which you get the kind of the right-left invariance, and at least if you project this diffusion on SL2, you do a QR factorization. So you mod out by SO2, so that, and you represent it via triangular matrices. Then I think it's identical, for instance, what you can find in the book of Lejean, who kind of on a very general, from a very general point of view, looks at these diffusions on Lie groups. And yeah.
Is there anything in 3D?
So some parts. So for instance, the fact that you, if you tune your drift to be critical, I think you can do many things in also in higher dimensions. What's not so clear to us, or at least not so clear to me at this stage, is how much of this structure survives in the three-dimensional case. So there are some there are some magic identities in the 2D case, which I don't know how they would turn out in the 3D case. But I think it's interesting to look into that, because in principle this kind of borderline homogenization, scale by scale, I think that would work in any dimension, provided you tune your covariance decay of B in the right way.
Very good.